Okay, as you go through U2A3, they're going to jump back and forth between electron configuration and quantum numbers, split them up into two separate thoughts. Electron configurations, I think I gave you everything that you need to know to be able to do electron configurations. Think of quantum numbers as another way of expressing the same thing, just like we can speak in English or we can speak in French. So what I want you to do is I want you to have a periodic table handy that you don't use for anything else but this. So I'm going to teach you what NL, ML, and MS means, and then I'm going to do 3 examples from 3 different areas of your periodic table. Now, the first thing I need you to do is take your periodic table and split it up into 3 regions. These are your S's right in here. So these 2 columns all the way down are your S's. And your S, your magic number is 0. These elements over here are your P's. So these 6 columns all the way down, these ones are P's and their magic number is 1. Then these columns in here, so I'm going to go right over from here to here. So this whole box here, these are D's and your magic number is 2. You just have to remember those or memorize those. S, P, D, and F, they're going to be very important. So for everything there are 4 quantum numbers. This is the energy level that they're in, and I'll show you all of these when I do my 3 examples. These here are your areas like your S, P, D, and F, so they are your orbitals. S, P, D. We're not doing F, so you're either going to be a 0, a 1, or a 2. These are your suborbitals. Remember when I drew the p orbital and it had 3 different sections like this? So this orbital is, the p is made up of 3 different suborbitals. I'm going to say something, I hope you catch this. When we have an orbital 1, the suborbitals can go from the negative to the positive of the 1. So we can have -1, 0, or +1. That's p orbital, has a magic number of 1. There are the suborbitals. Note there are 3. D's, we can go from the negative to the positive. That's 5 suborbitals for the D's. If you remember doing box diagrams, there were that 1D box was split up into 5, -2, -1, 0, 1, and 2. Now, ML means magnetic. So the way that scientists did this was they took the orbitals and they used strong magnets to split it up into suborbitals. MS is spin, magnetic spin. Electrons are either going to be a +half or a -half. So electrons don't just have charge, they have spin. Really interesting thing with Einstein, when I drew those diagrams that looked like this, where I started doubling up the electrons, these electrons are called entangled. We can remove one electron and we can transport it to the other side of the moon, and these 2 electrons can still talk to each other. If one has a positive spin, the other will have negative, and vice versa. This is called spooky interaction at a distance, and this was coined by Einstein. So far a lot of blah blah blah. This is all background information. Let's try and use this. So for each one of these elements, we're going to have 4 quantum numbers. The first quantum number is going to be your energy level. So what we do is we find magnesium. Magnesium is right there. It's in the 3rd period going across. So its first quantum number is 3. The next thing we have to do is figure out whether magnesium's in the S, P's, or D's. It's in the S's. We said S's magic number was 0. So remember I said S was 0. So its second quantum number is 0. If it's got a second quantum number or orbital of 0, its third number will also be 0. This will make more sense when I do other things here. Now, when I do my other examples, I'll explain that third quantum number. But if your second quantum number is 0, your third quantum number is 0. Now, is this a positive or a negative electron? The first one's always positive, the second one's always negative. So this one is -1/2. There are 4 quantum numbers. Let's try nitrogen 7. Your first job is to locate the nitrogen. It's right there. If we backtrack, nitrogen's in the second row, so its first quantum number is 2. If it is in the P's, its second quantum number is 1. Here's where things get a little trickier. You must be able to draw the box diagrams now. Because we're in the P's, we're drawing the box diagrams like this. Nitrogen is the 1, 2, third one over in the P's, so we give it 3 electrons. Remember, 1 electron in each box. Remember how I said the P's were split up into -1, 0, and 1? Just do this with your drawings. There's the last electron we drew right there. So we are in the +1, and it is a +1/2. We know it's +1/2 because it's sticking up. Let's say that we were doing fluorine. I just want to repeat this. If we were doing fluorine, and it is the 5th one over, we would go 1, 2, 3, 4, 5, circle the last electron you drew. So for fluorine, my numbers would be 0 and -1/2, okay? Because this one's facing down and it's in the zeros. One more rule to learn. If we're doing anything in the D's, we must do a drop-down rule. I'm not going to explain this one because it would be complicated and it would take some drawings, but as you go from the P's to D's, you got to drop down 1. So your first quantum number goes down by 1 from what you would think it is. You would think that for the B, that it is a 4, but it is a 3. It is in the D's, so it is a 2. That's my second quantum number. Now I have to draw a box for the D's. Remember, for the D's, this is the D orbital with 5 different suborbitals. Vanadium is the 3rd element over, so I go 1, 2, 3. I label my boxes. The middle is 0, and I work my way out. The last electron that I drew is in the 0, so that's my 3rd quantum number, and it's facing up, so it is +1/2. Folks, you will not have to do any drawings in the S, or in the F's. You're only doing S, P's, and D's. I like the way that I teach this better than the way that your content does, but hey, you feel free to use what you want to use. I like using the periodic table as a giant cheat sheet to try and get my answers. These are called quantum numbers. Now, I want to go over one concept that I missed from before. It doesn't matter what you're drawing, you always start from the beginning. This is called the Outbound Principle. So always start from the very beginning. So the first thing I wanted to mention is what the Outbound Principle is. So I add 1 positive and then 1 negative electron in. Now, the next thing I want to talk about is the Hund Rule. The Hund Rule states that we add 1 electron to each box before we start pairing them up. Okay, that's the Hund Rule. They're going to say it a little differently in your content. I'm just paraphrasing so you can have another look at it. Pauli exclusion principle says that you can't have more than 1 electron in one spot. So this is a placeholder spot. You're only allowed to have 1 electron there, 1 electron there, 1 there, 1 there, 1 there, 1 there. So Pauli exclusion principle just says you can only have 1 electron in a spot. Now, the Heisenberg uncertainty principle. When I draw all these nice, neat little diagrams, and I say the electron's there, basically what the Heisenberg uncertainty principle is saying is you can't say that the electron is right there. You can say that there's a probability that it's going to be anywhere in this space, but not exactly right there. I have paraphrased all of these rules. Take a look at the content, compare it to what I said to what they said, and formulate your own thoughts in your brain.